Hello, everyone. Good afternoon or good day to us all. Thanks for joining. We're going to go over the BLDC motor controller. This is part two of it. What we intend to achieve today, basically go over the circuit diagram, do some explanations, then go over the circuitry itself. Then we'll just go over some few aspects of the code base that relate to the circuit diagram itself, right? So is what we're going to do. So I'm going to share my screen now so that we can start off from the circuit diagram directly itself. I'll just do some explanations from the circuit diagram. And I believe we can take things from there. So give me a minute. I will um, share my screen. And thank you guys for coming around. It's really appreciated. And sorry for starting off late also too. Okay. Share my screen. Entire screen. Okay. Um, can you see my screen?
Yes, it is visible.
All right. Thank you so much. So the system we are working on basically is um, the whole idea of the system in general is basically it's an ECU as the end target, right? ECU. So the first goal we had in mind was to actually set up the controls of the motor itself. We're not focusing on the protective circuitries like shunt circuit, reverse polarity, overload, and the rest. No, the focus is just to have a circuitry that actually controls the BLDC motor, no matter how small it is. Because one thing I've come to understand is that in software, whatever works on a smaller motor, 9 out of 10 times works on a bigger motor also too. But in the hardware, you must tweak your hardware, you must adjust the hardware. But for the software aspect of things, whatever was on a smaller motor, that same code base can also work on a bigger motor. So that's the push we had towards this, right? So it's what we did. Currently, I purchased the 48 volts, 450 watts BLDC motor, the sensor BLDC motor, but I'm still having logistics issues from AliExpress, although I purchased it about 2 weeks ago. It's not yet arrived. We have just do the test for the two of them, but hopefully in our last section we'll have that test. We'll have that test itself. All right. So okay. So let's go over. So I believe we know about the STM32 controllers, right? This is my favorite controller, the F103C86, because it's very popular and it's what I actually used to start off my STM journey. So I kind of like most I used it for smaller projects, right? So when I want to work with BLDC motors, right? One thing we always put in mind is the sensor, the drivers, the MOSFET drivers, because it's either use IGBTs or use MOSFETs as your switches when you are switching, right? Which is here, right? So the kind of driver you use, the kind of motor driver determines a lot. For example, if you're using the IRO 2110, you need to have what's it called? It has the inputs and the inverted inputs also, meaning that if you send the a one, the second input you expect is zero, so that the output will be inverted also too, right? But I personally prefer using autocouplers, because for one, where I am based, where I am, a lot of components, usually, especially ICs, they are not original, right? But I was able to get a vendor that sells me original components, and that's why I focused on using TLP 250 directly itself, right? So what I want from, since I'm having a motor controller, BLD, a three-phase BLDC motor controller, what it means is that I'm going to have three half bridges, or three half bridges. Yes, three half bridges, right? Which is what we have here. This is one bridge. This is another bridge. This is another bridge, right? So what it means now is that I have to have three PWM, PWM1, PWM2, and PWM3, right? Now this PWM itself is also going to have what's the word again? Is it inverse? No, not inverse. I think it's complementary. Yes, complementary. That's what complementary, right? So my PWM 1, 2, and 3 actually have complementary pin. So my PWM1, that is PWM1H, PWM2H, PWM3H, actually these what's it called, P8 pin and P8 actually timer 1, channel 1, timer 1, channel 2, and timer 1, channel 3. Whereas the complementary of it is timer 1, channel 1 inverse, timer 1, channel 2 inverse, and timer 1, channel 3 inverse. So I'm going to use both of them to carry out this operation, right? In complementary, what's it called? Using, let me share my screen, switch my camera. I'm currently using, um, what's it called? I'm currently using the blue pill itself, right? What I'm currently using, and I want to share the picture of the blue pill itself, right? So that you can also see the pinout for the blue pill itself, So that's timer 1 for my generation, right? Then I send this to my drivers itself. I'm using the TLP 250, and this is why I'm even having complementary, because I think there is a, I think IR 21, I think IR 21, 2113 or so. No, IR 21, IR 21, IR 21. Yeah, I think IR 21 or so. IR 2113 or so. It has just one input. In the output, you now have two outputs, meaning that if I should send the one to one input, my output now we have 1 and 0. If I should send 0, it will have 0 and 1, just the inverse like that. If I were to use that what's it called, what's it called, IC itself, or that control MOSFET driver itself, I would just have to use just my timer 1, channel 1, channel 2, and channel 3, because I know if I send my channel 1 to the IC itself, definitely it is going to give me two outputs. So it collects a single input and gives out two outputs. That is for the the IC itself. But like I said, I prefer using TLP because that the IC itself is easy. Is if one should get damaged, it's a problem because I have to now change the entire IC for just one channel that gets damaged. While for TLP, this is single, can easily change the ICs if one gets damaged and do what I need to do. Right. So that's why I prefer to use TLP. And on that thing, since an auto coupler, there's isolation, a lot of isolation on it. Right. So that's how what I generated from my STM32. But the thing now is that my STM32 actually generates what's it called? Generates 3.2 volts output, right? Because a 3.3 volts controller. So the output is at most 3.3 volts at the output of my PWM itself. But I prefer to have a 5 volts at my output directly, not a 3.2. So what I did then was I decided to send it through a voltage level shifter, right? That's why you see PWM1, PWM2, PWM3H. I send it through this pin here, right? This is PWM1 low, PWM1 high, PWM2 low, PWM2 high, through this NAND gate level shifter. So what I'm doing now is that my input is 3.3. My output is 5 volts, right? Which is like more like a level shifter I used in the what's it called in the what's it called um in the design itself, right? But for the what's it called um the blue pill is the blue pill device, it has no level shifter on it directly, right? So usually you can just send the signal to your TLP directly. But one thing I observed while I was working on some inverters was it's always good to use the level shifter in between your microcontroller of 3.3 volts and something else, because if, for example, your MOSFETs get damaged or something, your TLP may get damaged also. It may affect, may reverse back and affect your pin for your microcontroller. And that's what I always try to do. Is I always try to, put like a middleman between my STM and my driver chip itself. Usually I like using this level shifter itself, right? Which is what I like doing here with it. Okay, which is what I did here. And this is 74HC132. It's really, really um, um it does the work really well for me, right? Which is why I choose to use it. Let me just quickly show you. Just give me a minute. Let me show you the design I had with it. All right. Okay. So I believe. Um, okay. I believe you can see this, right? You can see my camera, right? So this is the chip I used for which I want to use for the control, generally the final control. And I have an XTMF 103. Is it, can we see it? Is it clear enough? I doubt. Anyways, so these two chips here are the 74HC132. Right, so I send my signals from the chip itself, right, to the chip to NAND gate, and the NAND gate now talks directly to my TLP. And when I was choosing this, I also tried to ensure also too that the NAND gate switching, the response is also very, very important also too, right? The response time is very, has to be very, has to be sure, has to be very important. The switching speed, the frequency that you can actually switch, it's actually very important also too, right? Which is what I also put into considerations also too, right? So I send in my PWM1 through this pin here. Out of my pin 6, I get my output, LO1. Just let me try and share the screen itself of this. You better understand 74HC132. Okay, so 74HC132. I'm going to open up an image now and share. Just let me share it. Let me try and share. Let me see if I can open it itself. Okay, I think this is it. Can you see my screen? I believe you can see my screen. So this is the chip I use itself, 74HC132. It's a NAND gate itself, right? So it's what I actually use, right, to guess what I want. So pin 6 is my output. So pin 4 and 5 are the inputs, right? So if you observe here, you can see that um yeah myself. Okay, so pin one, pin 1 and 2, right, are the input. Then pin 3 is the output. Then pin 4 and 5, right? Oh, sorry, I'm showing you something else. Sorry about that. Okay, so pin 1 and 2 is the output, right? Let me see if I can take this a little bit now. Alright. So pin 1 and 2, right, is the input, right? Then pin 3 is my output. Then if you observe my schematic diagram, you can see that I now still send the output from my pin 3. I send it back again now to have these two inputs, right? These two inputs, 4 and 5, are now my input from my pin 3, my output of these two. And my input from pin 1 and 2, you can see that I'm sending 5 volts to it. Now, if you send 5 volts here, 5 volts, and let's say 5 logic high here and logic low here, right? Expect that from a NAND gate itself, if you have a 1 and a 0, you should have a 0, right? But a 1 and a 0 in this case is going to give me a 1, because I'm what's it called? Is it nothing nothing the AND gate, right? So if I'm to have a 1 and a 0, to have a 0, I'm going to have a 1 because it's a not at the final output. Which is just basically what I just did, just to have a level shifter. So the output of this guy now that goes to my TLP is going to be 5 volts. The voltage level is going to be 5 volts, no longer 3.3 volts. So that's how I was able to achieve level shifter for this, right? I'm sure it can be done with normal transistors also too, but I think I saw this from a reference design, so I just decided just to use it, and so far it's been working very well for me, right? So yeah, so that's it. Then from there, we now come down to the MOSFET driver and the MOSFET itself. So I believe we are aware of the TLP 250 itself. Right, so pin 2 and pin 3 are the input, then pin 6, 7 is the output, then 5 is the ground, based on how you want to connect it, right? So what I have now is low, high, low, high, low, high, right? Low, high, low, high, low, high. So this section here is one half bridge, right? This is under half bridge, right? And this is another half bridge also too, right? So um please give me a minute. Let me share something quickly. Okay, so so now um this is my U, right? Where the high and the low meet, where the source of the high and the drain of the low meet, that is where I pick out my first output. The same thing for this also too, and the same thing for this also too. It now goes to my motor. This is basically not really the motor, but I just put it there just to signify that it's actually a motor, a three-phase motor itself, right? PWM three-phase motor itself, right? So I have my U and my V and my W. So that's basically just the simple and what's it called work around this. If we were to go a step further, right? For example, let's see how can we to monitor what's it called, let's say shunt, because it's always good to monitor the current on each phase, right? What I'll just do there is I'll just um take this and just apply this here, right? What you're just going to do is just to have this here, right? Then maybe here will not be there. You should shunt this stuff around, let's say 1 milliohm, or let's say 3 watts or so, or 2 watts or so, 1 milliohms, right? Then I'll not be able to read from this point here, take it out. I'll just have something out from here, right? With this now, I cannot be able to read my shunts for this particular U phase. I'll do the same thing also too for every other phase. That is low current sensing, right? Low side sensing is what I'm going to do there, right? So that is it for this, right? So let's quickly, I don't know. Okay, I think we are just the ones left here. No. So no, you have any questions so far? Are you with me? Hope I'm even audible. I don't know. Are you there? Am I? Can you hear me at all? It seems. Hello, Mr. Noah. Are you with me? Sorry, I'm pronouncing the name wrongly. Can you hear me loudly? Can you hear me well? If you can hear me, you can type or respond or something. Uh, am I still audible? Since my network is bad. Okay. Any questions so far? What is happening? To. I can't seem. Okay. Uh, okay. I will proceed. Right. So that's just how this guy is wired up. Right. That's just how it's wired up. So let's just quickly go and observe the circuitry itself. Okay. So I believe my screen is visible to an extent, right? So currently I have my power pack, right? I have my power pack connected to the device, right? So it's let's have this here. So I'm going to turn it on now, and this is the motor itself. This is not that clear. So what I did now was I actually am using. This thing is not clear. I need my camera. But that point is clear. It is clear, man. But it's not clear. All right. So I don't know. Okay. So what I have an EDC. I have an EDC. How is it not clear on this? This this guy here, right, is actually what was it called? It's actually being used as a potentiometer to vary the speed of this or the motor itself, right? So if I do this, right, I'm going to reduce the speed of the motor. I'll try to see if I can uh, reduce the motor speed. So I've been able to reduce the speed a little bit, right? So I don't know if I don't know if you can see. I don't know if you can see. So that's that, right? So I've been able to actually, come up with this. So yeah, this is actually using the SPWM to do what needs to be done, right? To do what needs to be done. But the end result of all this or everything that we intend to do is basically to use what is it called? Um, what is the name? To use FOC at the end of the day to actually do some controls on this motor itself. Right. So that's the end goal of all of this, right? So yeah, that's what we have currently here. Currently working for us here, right? That's what we currently have, and yeah, I feel. Do you have any questions we need to share? We'll talk about. It's going to be a nice time for us to talk about those questions. Right. Before we move on to something else. I don't know any questions. Okay. Since there isn't any questions, so I think that's fine. Yeah, I think that's fine. So I think we can end the session here now. I can end the section here now, and thank you guys for showing up. For those who showed up, it's really much appreciated, and looking forward to having the next section itself with you guys.